And I'll rely on chat to let me know if you can't actually see anything, but in the interest of time, I'm going to move on. So for those of you who aren't familiar with the graphics background, I haven't actually been able to visit many data centers due to the pandemic. So all of the graphics for the talk today came from my pandemic island on Animal Crossing. So if you're wondering, that's where all the pictures are coming from. So the other thing that I've started to learn from doing talks this year is that people can kind of get a little bit burned out on Zoom, particularly if you're in all day. So we're trying a little bit of an experiment.
Yes, we can't see your slides.
All right, so let me go back here. Let me know if, let me know if that's visible now.
Yes, that's perfect.
Okay, yep, sorry about that. So yeah, in the interest of time, we're trying a little bit of an audience interactivity thing. If you feel like going over to slido.com and entering the code TFT, you'll be able to participate in an audience Q&A, ask some questions. That being said, Zoom chat is still totally viable. And what we'll be doing is we'll likely be curating questions that come in via Slido, and we'll just be pumping them into chat as well so that Kevin only has one place to look. So just by way of interaction, this is the type of thing that Slido allows. We can sort of embed live polls, quizzes, and surveys into stuff. BioTeam has found that it's fairly useful when doing sort of live remote virtual sessions over time. But oh, look at that, someone just answered the poll. So I'm not going to belabor this, just to show you that it's kind of cool to add sort of interactive data gathering stuff to a long talk or a long session. So I'm going to skip the audience survey. This is just an example of embedding some of the Slido stuff into a talk. And by way of introduction, I actually don't think I need to do much of an introduction since Cindy and Kevin both did it. But yeah, 11 years ago, this was me. And unfortunately, I sort of created a monster. I think, like as others had alluded to, one of the reasons why the Trends Talk became popular is that the cool thing about BioTeam and our work is, we're consultants. We're in and out of many, many different types of organizations every year. We get to see how similar groups of people, similar groups of smart people tackle similar problems. And so, and also many of our customers, many of our projects, we're allowed to publicly disclose certain things about what we see. So I think way back in 2009 and 2010, people sort of liked the blunt and honest. I was fairly candid about the things I screwed up. I was fairly candid about the stuff I liked and I didn't like. And, I think that was a relatively refreshing view for conferences where, there might've been a bit of a marketing spin or, that sort of thing. So that's sort of the background of why I've sort of been doing this for the last 10 years or so. And I'm trying desperately to pass the baton to younger, smarter, more accomplished people than me over time. And neither BioIT nor Stan will let me. So again, we accidentally created a monster. And again, this is now the 10-year anniversary, but everybody has gone over that and I'm already more than embarrassed. So I'm just gonna go through that very, very quickly. So the other thing is that because we're meeting virtually, we actually have the ability to bring a lot of our friends together. So I really want to highlight the sort of high-powered panel we've got. And my goal really is to sort of do my standard thing where I speak very, very quickly and stun you senseless with a ton of slides, but then get out of the way relatively quickly so that I can hand over to the panel and we can have more of an interactive discussion back and forth. So quick, the way that what I want to run this, the original Trends was sort of a solo act. I would do 90 minutes. I would slam 180 slides down your throat and then, we'd call it a day. But it's time now to sort of switch up the focus. I don't have a lot of time to do a deep dive into multiple topics. I could talk for 30 minutes about cloud or storage or infrastructure or GPUs alone. And, we simply don't have the time to do that in our forum. So what I'm actually going to do is change it up a little bit. I've got a couple of sort of very quick hit topics to cover. I'm going to talk about some of the drivers that are changing IT and infrastructure this year in 2020. I'll talk a little bit about the hype warning for 2020. And really, I'll be candid about all the stuff I got wrong last year in the Trends Talk. And then I'll take a slightly deeper dive, spend a little bit more time in the talk on just one major topic area. And both because it's a major focus of our consulting work, but also because of the makeup of our panelists, I've chosen this year to focus on storage and sort of data management and data exploration and data insight topics. And so with that said, let's be going. So the first quick topic that I want to cover is really, what are the scientific drivers that are stretching and altering sort of IT requirements, architectures, and needs over time. And the following couple of slides I'm going to show you is really a distillation of multiple BioTeam consulting engagements over the last year. And so just to be very clear, this comes from BioTeam. This is not my work. There's a ton of really, really smart people producing really good information, and I'm lucky enough to be able to plagiarize their work and stick it into my talk. So, starting from the sort of first and original driver, we still have genomics and bioinformatics. Historically dominant and still very, very large player in the infrastructure space, particularly because sequencing just keeps getting bigger, faster, cheaper, and more accurate. And every time that happens to an instrument, you see sort of a reset in the type of scientific questions and the sort of depth of scientific exploration that's undergoing. The IT impact for genomics and bioinformatics, though, hasn't really changed. It's really about having enough storage capacity, petascale in many cases, and having a mix of large memory, regular memory computing, and also a lot of the IT and infrastructure challenges around genomics right now involve actual data movement and data capture, because the source of our genomic sequencing information is coming from all over the place. It's coming from the edge of our enterprise over the network, but it's also coming from outsourced CROs and data providers and things like that. If we move on to the second biggest driver, this is actually the fastest growing IT driver that BioTeam has really ever seen. It's really interesting. If you do a storage audit or storage analysis in a scientific computing environment, particularly in sort of a data intensive life science organization, the dominant file type is now images. The dominant file type used to be reference genomes and genomes. We're now clearly seeing that the fastest growing driver, and in many cases, the dominant type of file, is actually image. And so what that actually drives is, it drives, again, an interest in storage capacity. We're starting to see a little bit more focus on the performance of storage, because image-based workflows tend to be fairly IO bound if they're not memory or GPU bound. Definitely, this is where GPUs come into play. There's a lot of the analysis workflows, particularly for cryo-EM, that quite a bit of the analysis is offloaded to GPUs. And then finally, the images are just as big and coming just as fast as genomes and genomic data. And so again, from an IT and infrastructure perspective, there's a renewed focus on the speed of our networks, the cleanliness of our networks, and how are we doing large-scale data ingest and data movement, both within the organization and through firewalls and to and from various clouds and collaborators. Machine learning and AI is actually the toughest thing. So the problem that we have with machine learning and AI is that with the other types of science drivers, as an IT person, I can often make trade-offs. You know, I could have an honest conversation with bioinformatics people and say, look, I can give you a giant storage system, but it's not going to be the fastest system on earth. And so they would make a trade-off because they needed capacity and they're willing to run a little bit slower, or maybe they weren't even IO bound. The problem with machine learning and AI is that it is radically changing the storage that we design for biotech, pharmaceutical, government, and EDU. We now need to have storage that is both very, very fast and very, very big. It's tough to have a thin wedge of really fast performance tier and then a bigger wedge of nearline and a bigger wedge of archive, because in machine learning, you're constantly going back and you're training and retraining your model against both old and new data. And so if you look at the IO usage patterns for machine learning and AI, not only do they need very, very fast storage because they're actively analyzing new stuff, but your storage namespace or your storage platform needs to be very, very large as well, because they're often reaching back in time and they're constantly rerunning against older data. And so that's probably the biggest IT challenge that we have right now as the rise of machine learning and AI. I used to be able to save money by picking one, big or fast. Unfortunately, with ML and AI, I need both. I need big and I need fast. And that's why you're seeing some relatively interesting movement in the storage space in life science. There's some historically dominant, scale out NAS vendors that are have some competition now, and it's fairly sort of interesting to see that in the real world. And then finally, chemistry and MD is interesting. Again, the focus there is really far more CPU bound and GPU bound than storage bound. It's also a particularly good sweet spot for moving to the cloud, particularly if you don't have latency sensitive or 3D sort of information to sort of deal with. Interesting data point, I was looking at the sponsors today and really just looking at, so this is all the sponsors that we have for BioIT World right now. If I subtract out and just try to highlight the ones I think of are explicitly storage players, there's still a really interesting mix here. And then if I look at the ones that are explicitly here and offering a data management, data analysis, data movement, or sort of data exploration service, we have another set of vendors. And if I combine the two, we actually have a fairly interesting, solid majority of BioIT World spenders are playing in either the storage or the exploitation of knowledge space. And so it's notable because the focus of this talk is really data and data management, so I think it aligns. But also, this means to the audience here that if these topics are of interest to you, there's a lot of really interesting vendors that you can go talk to. And I'd encourage you to sort of take advantage of the conference virtual trade show booth, virtual expo floor hall. Every one of these vendors here would be happy to chat with you and sort of answer questions. So that was sort of the scientific drivers. That was kind of a recap of things that are sort of driving IT and infrastructure in our consulting world. And basically, the type of science that you do influences the type of IT and infrastructure that you need. And really, it's irrelevant whether it's cloud or on-prem. The stretches are the same, regardless of the location of the compute or the storage. So moving on a little bit on sort of puncturing the hype curve. Every year, there's a new bandwagon. Every year, there's a new hype thing. And every year, we try to puncture the hype a little bit. And so, I really wanted to sort of punch this up. And so I'm going to sort of title this as what are vendors most likely to lie about in 2020 and 21? And many of you can probably guess the answer, but it's machine learning and AI. In every purchase cycle, there's breathlessly overhyped product. There are manufactured reference cases, things that really don't add up when you sort of read between the lines. And so The machine learning and AI space has been like this for a long time. It's basically creeping in as a buzzword into every product sheet that you can imagine now. And also that last bullet point there, I don't know why, if it's because they hire super aggressive salespeople, but you know, when you're dealing with the super hype products, that's also when you end up with kind of a really creepy and unprofessional sales cycle. And I like to call that out when I see it. And yeah, there's a lot of tech bros doing weird stuff in the ML and AI space, particularly trying to sell to you right now. That being said, I want to be absolutely clear that unlike blockchain, machine learning and AI is actually useful. These methods are real, beneficial, and sort of driving real significant transformation in life science. So the issue here is you've got to apply your sort of conservative cynicism to sort of filtering out what's realistic and usable to you versus, you know, what is kind of wrapped up in sort of a big fluffy marketing ball from someone trying to sell you stuff. So just be cautious, you know, test the reference cases, make sure it's not a fully manufactured reference. And then the other big thing is the way these products are sold. Machine learning and AI is probably something that needs to be driven from your engineers and your scientists at the bottom up, because there's a lot of decisions that need to be made about what does your tooling look like? What is your workflow? What inference engine are you going to select? What framework are you going to choose? What GPU family is you know, most efficient for the type of work that you're doing? The problem is that the sales cycle is often focused on selling to the senior people. They're selling into the C-suite or trying to sell into the board. And so you've got to manage a little bit of expectations where you might be getting pressure from senior management who are trying to push a very, very large ML and AI push down into your world, when in reality, it's actually the scientists and the engineers and the software developers down in the trenches who probably should have a little bit more say in those decisions. This is one of those topics where I'm sort of uncomfortable seeing the selling into the C-suite pitch. I think that the sales cycle needs to target the end users and the scientists rather than the IT and scientific leadership. So that was kind of the hype thing. Moving on a little bit to sort of scientific data here. The reason why I wanted to sort of concentrate a little bit more on data and data management topics is listed really here on the slide. One is that, you know, petabyte scale storage has been easy for a long time. Managing and understanding the data that you have is still the single hardest problem I have in sort of the bio-IT spectrum. It's a significant amount of our consulting work every year. And finally, we are seeing the limits of what can be done with scale out NAS. We're seeing the limits of what can be done with tiered storage or automated policies and things like that. And then finally, you know, the rise of ML and AI and its stresses on storage, including also the image-based acquisition, are sort of radically changing the sort of fundamental baseline requirements I had for designing and speccing out storage systems for research computing environments. So these are all of the reasons why it sort of makes sense to sort of concentrate on data storage and data management topics in this sort of shorter session. So our focus on scientific data, the problems we have is that we've got big data, we've got siloed data, we've got dirty data, and we've got biased data. And I'll try to talk a little bit about each. So the issue with big data here is, you know, if you listen to me, and you're probably tired of listening to me after 10 years, I used to say a lot of stuff, you know, like it's far easier to acquire or generate data than it is to efficiently store it over its full life cycle. It's also been, you know, I've said this repeatedly, that although storage is decreasing in price, it's not decreasing fast enough to compensate for the rate at which we're acquiring, generating, or downloading new data. The issue here is in 2020, cryo-EM and sort of image-based workflows have sort of blown that out of the water. The issue that I'm really seeing here now, and this is where I'm going to be blunt and sort of call out failures in scientific leadership and IT leadership, is for too long and for too many years, leadership has avoided having uncomfortable questions with scientists about data stewardship, data management, and data organization. Rather than have that uncomfortable conversation with scientists, they've just thrown money and made their storage systems bigger. And we're now seeing some fairly problematic limits with this style. And I will reiterate, this is absolutely a failure of IT and scientific leadership. They are adverse to difficult conversations with scientists, and those problems are now coming back to bite them. So the other issue here is, I used to say, you know, if you had a petabyte of storage in your organization, you were at the level where if you didn't have a full-time human being managing and curating your data, you're wasting more in CapEx dollars than the cost of that human being. The flip side here is I've now seen multiple organizations with many petabytes of data who have no curator, no standards, no governance, no quota, and no policies. And so we're now, I'm sorry, I used to say, you know, at 1 petabyte, you need a human. Clearly people disagree. I'm seeing people with 10, 15, 12 petabytes out in the field, and just a long history of just absolutely ruddership leadership when it comes to sort of organizing, managing, and sort of curating that data. I really do think, I used to say in the years past, data triage was okay. We've in genomics in particular, we've gotten comfortable with deleting data because we can always go back to the -40 freezer and rerun the experiments. We have a history of our instruments getting better and more sensitive and being able to run the samples that we have. Typically people are a little bit more comfortable with throwing away old data because they can either regenerate it or they can rerun it. I'm also very, very well known for being very blunt and stating that it is wildly inappropriate for IT to have a say in scientific data management decisions. Any data deletion, any data triage decision has to come from science, and it has to be governed on the science side. It's really, really inappropriate to bring IT into the mix here. So it's a difficult thing to manage. But if I contrast that to stuff that I'm seeing now, just broadly speaking, collectively, we've sort of failed at this. I think the time now is new and sterner methods are going to be required. There are some intractable problems, and you really can't throw money at the issue anymore. You can have as many petabytes as you want, and your scientists will always find ways to fill it up. So we really, really, really now need to be talking about data management, data stewardship, and data governance. So I'm trying to create a new trend in 2020, and this has sort of permeated my consulting work over the last year. I really want to push a culture change across the life sciences and realistically sort of push across the point that storage needs to be treated just like any other lab consumable. You need to justify it, you need to budget for it, you need to plan for it, and you need to be able to defend that to your leadership. And I think that it needs to be actively managed by both science and IT. And one of the ways that you're starting to see trends like this sort of manifest in the real world is this is coming from NERSC, and I've got a slide coming up, but I really, really like it. One of the single biggest issues that we've seen is sort of unrestricted growth in people's home directories and personal folders. You end up with data attribution, data versioning, even data fidelity questions. And so one of the really interesting trends we're starting to see here is nobody gets large storage anymore. Nobody gets a personal folder that's giant anymore. All storage allocation is handed out on an experiment or project basis. And that single change alone is driving really, really interesting and positive changes. No more giant home folders. All storage has to be allocated or binned out and assigned to either a project or an experiment. And you organize at that level from the top down, and it works out a lot better. You have far less islands of data where you really don't know what's going on and what that person has done in their home directory and how those permissions are constructed and everything else. So this is just an example, just trying to show you that this is out there in the real world. It's really interesting. I like reading file system and other acceptable use policies at supercomputing sites and other sites because, the people who have much larger infrastructures than us that have much bigger problems to solve, none of this is rocket science. Other people, other industries have solved the same problems that life science has. So I'm looking at things like NERSC and I'm like, wow, okay, you flat out don't get more than 40 gigs in your home directory. You flat out don't get more than 1 million inodes. That's the type of sort of practical, sort of real policy-driven stuff I like to see. Again, NERSC is doing this because all of their storage allocation is dedicated to something that's not a personal home directory, basically. If you've got big data, you got to put it somewhere else other than your personal folders. So moving on, talking a little bit about siloed data, the issue here is, collectively in the early days, in the 90s and early 2000s, we used to be able to centralize compute and storage. We could put it all in one data center. We could bring the users in over a VPN or a remote desktop session. That really doesn't fly anymore. Data-rich environments are sort of diffused throughout the organization. They're at the network edge because we've got terabyte-scale laboratory instruments and satellite offices. We've got data sources that are all over the world from collaborators, outsourced data providers, CROs. And it's not just static files anymore. It's not images and genomes. It's events, it's documents, it's IoT, it's time series sensor data coming off of bioreactors, all sorts of sort of rich data types that we have to capture, analyze, and manage. And finally, the last bullet point is significant, is that there are now petabytes of really interesting open access data that would be completely viable for a scientist to want to download and bring into her working environment. So IT now has to sort of deal and game out and plan for the fact that not only do we have to deal with managing storage, compute, and analysis for our own internally generated data, we also have to sort of carve out the ability for our scientists to bring in really just truly vast amounts of public domain data down so that they can be sort of integrated and computed against and, analyzed and exploited. So what we're starting to see here is, from the infrastructure perspective, this means, again, BioTeam is doing networking. We're separating science data from business networks via science DMZs. We're starting to see more 40 gig and 100 gig networking segments being run inside companies. We're starting to see a lot of compute, or at least initial compute and transformation happening at the edge before it sort of goes into the central scientific analysis environments. Data lakes are interesting. For every awesome data lake project, there's probably a dozen or so sort of embarrassing failures that are sort of hidden away and no one really talks about anymore. And then finally, the really interesting thing here is the trend around data platforms and data commons. And just to highlight, BioTeam has sort of settled on the open source Gen 3 stuff. And I left a couple of URLs in there, but one of the other things that's interesting is I just did a quick hit through the agenda at this particular conference, and there was at least 3 talks alone, and I might have missed more on Gen 3. And the cool thing is all of them are available on demand and they're recorded. So if Gen 3 and data commons is sort of interesting, definitely take advantage of the conference platform here and go check out some of those talks. I think most of them have already happened. There might be 1 or 2 happening more today. Finally, sort of transitioning into dirty data. So the issue that we have here is, and I've seen this personally, I'm not going to tell you my age, but in one career generation, I've gone from sort of tracking data in a scientific lab notebook in a wet lab to sort of petascale data wrangling. And so generally speaking, we've scaled up our storage capacity, but we've ignored or underinvested in everything else. And that's governance, curation, metadata, data cleaning, SOPs, and standards. I've already repeated myself here, but I will say it again. The blame lies with scientists and scientific leadership. IT can't make these decisions for you. It's on you. It's up to you to clean up your stuff. It's up to you to manage your data. And we're starting to see the effect in our consulting work of years or decades of neglect of storage management. And it's becoming very, very sort of painful to deal with. It's also going to mess up a lot of ML and AI work because the accuracy of your ML and AI depends on the cleanliness and organization of your input data. And frankly, from what I've seen out in the field, it ain't that clean and it ain't that organized. So there's a lot of work that needs to be done. So moving on a little bit to the other big thing with ML and AI in particular is the problems of sort of biased data. And so, we as scientists, we as IT practitioners, we as people who are sort of involved in data intensive science, with a healthcare or mission to improve, human lives and human outcomes, it's our responsibility to ensure that this is handled responsibly. We've had clear failures with data hygiene. We've had clear failures with biased models. And it's really, really sort of up to us to make sure that the mistakes that other industries have made with ML and AI don't continue to percolate into sort of data intensive life science or sort of discovery oriented scientific research in general. And I suspect the high powered panelists that we've got here have probably got some interesting things to say about this as well. So moving on, I want to hit the other quick topic here, all the things that I've screwed up in the past. And so this is where I can sort of candidly go back on things that I said in 2019 and, tell you what I got wrong. The list of what I got right, I think, is much smaller. So it's easier to go through what I got wrong. All right, so this is sort of a short summary of things from past trends, and I've just got a slide on each of them, so I won't stick on this particular slide. So compilers matter again. So there was some interesting time when BioTeam was doing a lot of work with cryo-EM workflows, in particular figuring out that there were actually very significant performance differences depending on what compiler you use to build your open source scientific software. We saw significant differences, and we thought that those differences would justify a lot of investment in compiler work and optimization. Absolutely wrong. I was expecting a bunch of interesting consulting work involving, compiler and application deployment workflows, and pretty much none of that happened in 2019-20. I think people are still using, the standard tools, or they haven't really sort of changed up what they're doing with respect to compilers. The other thing is that, last year it was abundantly clear, and it's become even more clear now, that Intel has some very, very serious competition now. There's really not a clear answer to AMD EPYC for a lot of use cases. And so I also expected in my infrastructure work to expect, I was expecting to do a ton of, AMD versus Intel benchmarking, helping people make procurement decisions, especially as if you look at where the exascale supercomputing bids have sort of gone in the last year or so, there seems to be a clear trend here. But again, this is something that really sort of never materialized. It might have materialized elsewhere. So again, being honest, this is from BioTeam's consulting experience. Just never really saw a lot of compiler work in the last year or so in terms of our consulting work. Although I will say, now in 2020 and 2021, it's not just AMD versus Intel. You're starting to see, like, particular, if you look at the price differences on Amazon for the ARM64 options. So I'm not sure if I'm gonna, stand here and say that compilers or CPU stuff matters again, but the diversity of choices is even more beneficial now, or even more significant in 2020 and 2021 than it has been in the past. The other thing I used to talk about was I really wanted policy-driven automatic tiering storage, and I've completely changed my mind on this. I think what we found in the real world is that IT managed automatic tiering of scientific data based on some arbitrary policy like file age or last access time is really not ideal for our world. I've got some more stories about the time a 12 petabyte file system decided to archive all the bash RC files. Again, having IT or an IT administrator control the tiering process is not a really good fit for scientists. And really, I think what I wanted to say is, and I knew this for a long time, it just never really manifested in my thinking about storage and storage management. But The fact is, if you talk to a scientist and if you sit down with her and you ask her about how she manages data, it's very, very clear that scientists work on a project basis or an experiment basis. So rather than archiving or tiering based on file access time or age, which is not really good for scientists who often need to go back and reanalyze old data, to hit a publication requirement or something like that. What scientists really need to do is they need to make storage and storage management, and particularly tiering decisions, based on project or experiment. And again, that puts you clearly into the world where you're outside of what the sort of policy engines can sort of do in the standard projects. And we've got to give more control over the storage management to the scientists, because that policy-driven stuff based on artificial metrics like access time and file age, it just doesn't align with the way scientists work in the real world. So what I'm really pushing for and what I'm really looking for when I evaluate storage platforms is I'm looking for storage platforms that either offer really intelligent policy-based decision-making, or more ideally offer user self-service. Allow the user to tier or archive a giant directory without opening a help desk ticket. If she could just right-click and send a nearline, something like that would be ideal. Finally, I also talked about single global namespace. This is where I am going to get a little bit salty. From an IT perspective, a giant single namespace storage island is fantastic, because the less data islands you have, the less data duplication you have, the less questions you have about data provenance, or is this really the reference file that we should be using or not? But what I found, and this goes back to what I've said before, where years of real world data just kind of shows that end users are not really responsible stewards of the storage when they've been given a giant single namespace environment. And I'm going to be salty here and say that I'm really tired of hearing whining from scientists who built their entire career on publishing and being known for working in data incentive science, having to whine about sort of actively managing and make data-driven decisions about their data. I'm going to be clear here. As an IT person, I'm done. If your career is based on data intensive science, I don't want to hear you whining about the onerous burden of managing your data. That's your job. That's your job. You know what? Do your job. And it's starting to get fairly problematic in this space. And again, it's really coming back to just years and years of irresponsible stewardship and years of sort of failure of scientific leadership and IT leadership to have those difficult conversations with scientists. And now we're starting to see the problem. We literally do not have the budget, or we literally do not have the capacity to grow the storage to the rate at which the scientists won't consume it. So we actually have to have these difficult discussions, and we actually need to put the control back into the hands of the scientists. All right. Oddly enough, that's actually the end. And if I look at my timer, I actually ended with a few extra minutes to spare. So what I'm going to do here now is I want to thank you for your time, especially those of you in West Coast time zone, where it's still very, very dark right now. My goal right now is I'm going to shut off my camera, put myself on mute, and hand it back to Kevin. And again, thank you so much for your time and attention. Thank you for the opportunity for being able to speak with you today.